In this video, we are going to discuss on tutorial 21. The topic is work and first law of thermodynamics. Okay, question 1. The diagram shows 3 moles of an ideal gas which undergoes an increase of temperature from 310 Kelvin to 340 Kelvin at constant pressure 1.15 times 10 to the power of 4 Pascal after absorbing 1635 joule of heat. As a result, the gas expands from a volume of 0.061 meter cube to a volume of 0.099 meter cube. So calculate the work done by the gas, the value of the molar heat with constant pressure and mass of the gas, and the change in internal energy of the gas. Okay, and question D, the same gas at 400 Kelvin is heated at constant volume by supplying 2101 joule of heat energy. So calculate its final temperature. Okay, so first we check what is given in the question. So number of moles 3, initial temperature 310 Kelvin, final temperature 340 Kelvin, pressure constant 1.15 times 10 to the power 4 Pascal. So this one is absorbing heat, so that means this delta Q is positive, and the volume initial and the volume final. Okay, so calculate the work done by the gas. So for the work done, so we can use work equals to pressure times change in volume, because pressure is constant. So we use this formula, pressure and the volume change from V1 to V2. Okay, so we substitute all the values in the equation, and we get the answer 437 joule. Okay, B, the value of molar heat capacity at constant pressure. So for molar heat at constant pressure, we can use Q equals to NC, molar heat capacity at constant pressure times the change in temperature. Okay, so we rearrange the equation CPM as a subject, so equals to Q over N change in temperature. So we substitute this Q 1635, then the number of moles 3, and the change in temperature. Okay, so the answer is 18.17 joule per mole per Kelvin. Okay, next, to find the change in internal energy. So the change in internal energy, we can use first law of thermodynamics. So delta Q equals to delta U plus work done. So this one is change in heat, and this one is change in internal energy. So change in internal energy is equals to change in heat minus work. So change in heat is positive because this is absorbed, right? The heat is absorbed. So positive 1635 minus the work done is 437 from the question A, work done by the gas. So work done is positive because it's by the gas. Okay, so positive, negative, plus positive, negative, positive, minus minus positive 437. So the answer is 1198 joule. So this is change in internal energy, and we get positive value, so that means the internal energy increases. Okay, next, the same gas at 400 Kelvin is heated at constant volume by supplying 2101 joule of heat energy. Okay, so we use Q equals to N CVM delta T. We use constant, we use capacity, molar heat capacity at constant volume, because given here constant volume. Okay, so to find CPM, you can use CPM minus CVM equals to R. So the relationship between CPM and CVM formula. Okay, so we substitute the value of CPM just now. Now we get 18.17, okay, minus R 8.31, so you get the answer CVM 9.86 joule per mole per Kelvin, and we substitute into the equation, okay, the change in temperature. So the 400 is the final temperature, is the initial temperature, and N is 13 moles, okay, or 3 moles, okay, typing error there, 3 moles, and the Q is 2101 joule per mole, so there's typing error here. This N is supposed to be 3, so the answer is 471.03 Kelvin. So this is the temperature, so make it 3 significant figures because the temperature here is in 3 significant figures. So supposed to be 471 Kelvin. So that's the final temperature. Okay, next we go to question 2. Okay, for question 2, 4 moles of an ideal gas is cooled down at constant volume from 610 Kelvin to 550 Kelvin. A total of 5006.4 joule of heat energy is removed from the gas, and relative molecular mass of the gas is given 32. So state if work is done on the gas. Give a reason. Okay, so you are given number of moles for initial temperature, final temperature, and the Q is removed. So that's mean it is a negative, because the word here remove. So the Q is negative. So molar mass is given. The relative molecular mass, we use symbol M, capital M. So to check whether the work is done on the gas, and we refer to the constant volume here. So no work is done because constant volume. So no work is done on the gas. So this is because the volume of gas remain constant. Okay, next, find the molar heat capacity at constant volume. Okay, so molar heat at constant volume, you can use Q equals to M CVM delta T. Okay, so CVM is Q over N delta T. So delta T change in temperature. So temperature change final minus initial. So 550 minus 610. So the Q is negative 5006.4. And because gas, the heat is removed, so negative. And number of moles is 4. So the answer is 20.86 joule per mole per Kelvin. Okay, then B2. B2, we are going to calculate the molar heat capacity at constant pressure. So to find molar heat at constant pressure, we can use the relationship between CPM and CVM. So CPM minus CVM equals to R. So molar heat at constant pressure minus molar heat at constant volume. Okay, so we rearrange it. We get CPM equals to CVM plus R. So substitute this CVM into the equation here. Plus R 8.31. So the answer is 29.17 joule per mole per Kelvin. Okay, now we go to question D. Question C now. Question C. So question B2 done. Question C, determine the specific heat capacity at constant pressure. Okay, so specific heat capacity, we use symbol small letter. Okay, small letter specific heat capacity at constant pressure. So molar heat specific. Okay, this one is specific heat capacity, molar heat capacity actually at constant pressure. Just now CVM, now we are going to find CPM, molar heat. This one is supposed to be molar heat capacity. Okay, so we use CPM is C over N. Okay, so N is M over molar mass. Okay, then we C over M is C. Okay, the question asks for specific heat capacity, so we use small letter. So specific heat capacity is heat capacity over mass. Heat capacity over mass, because specific heat capacity is if we refer to the unit is joule per kilogram per Kelvin. So the kilogram is mass. So heat capacity over mass. Okay, so we replace C over M here with C. So this is what we are going to find. So specific heat capacity will be molar heat capacity over molar heat capacity over molar mass. Okay, molar mass. So we substitute the molar heat capacity at constant pressure. So at constant pressure, from B2 is 29.17. So we substitute into the equation, divided by molar mass 32, there 32, and we get the answer. Don't forget to convert uh, 32 gram per mole here into kilogram per mole. Okay, because this is relative molecular mass, so the unit is gram per mole. So to convert to kilogram, so we multiply by 10 to the power of negative 3. Okay, so the answer is 911.56 joule per kilogram per Kelvin. Okay, next, we can write it in 4 significant figures. Okay, 911.6 joule per kilogram per Kelvin. Okay, this is okay. The heat is given in for 5 significant figures. So we can also write in 5 significant figures. Okay, next, we put there the answer. Then D, calculate the change in internal energy of the gas. So change internal energy delta U. So we can use first law of thermodynamics. So delta Q equals to delta U plus work done. So delta U is equals to delta Q minus work done. So delta Q is negative because the heat is removed. So that means negative 5006.4. And there is no work done because the work done is 0 at constant volume. Okay, so internal energy is negative 5006.4 joule. So the negative means that the internal energy decreases. The internal energy decreases because we get negative. And it is logic because the temperature also decreases. So if temperature decreases, internal energy also decreases. Okay, now we go to question 3. Okay, question 3. A system absorbs 95 joule through heating. The internal energy of the system decreases by 15 joule. Calculate the work done by or on the gas. Okay, so you are given delta Q, change in heat. This is absorb. Okay, absorb means delta Q is positive. Okay, internal energy decreases. So decreases, that means this is negative 15 joule. And we're going to find the work done. So we use first law of thermodynamics. Delta Q equals to delta U plus work done. Work is equals to delta Q minus delta U, and we substitute these two values into the equation, and we get 110 joule. Okay, so that's the answer for question 3. Okay, next question 4. A fixed mass of an ideal gas absorbs 2100 joule of heat and expands slowly at a constant pressure of 1.6 times 10 to the power of 4 Pascal from a volume of 0.066 meter cube to a volume of 0.072 meter cube. Okay, find the change in internal energy of the gas. So you are given delta Q, and it is positive because of the words absorb here. Okay, expand slowly. So this one will be the work done is positive, and pressure, constant pressure, volume initial, volume final, and we are going to find change in internal energy. So from the first law of thermodynamics, delta Q equals to delta U plus work, and to find work equals to pressure because constant pressure, so we use this formula, pressure times change in volume. So we substitute the final minus initial volume, and we get the answer 96 joule, and it is positive because this is involved expansion, so we got positive W. So positive W, we substitute into the equation here. Delta Q positive 2100 minus 96, so we get 2004 joule. And delta Q is positive, we correct, because it is absorbed, so we got positive, internal energy is positive, so that's mean the internal energy increasing. Okay, next we go to question 5. 8 moles of an ideal gas are in a cylinder with a frictionless movable piston. So the initial temperature of the gas is 33 degrees Celsius. The pressure is kept constant at all times. Determine the final temperature of the gas after 2 times 10 cube joule of work is done on the gas. So you are given number of moles, initial temperature, and we are going to find final temperature, and the work done 2 times 10 to the power of 3 joule. So work is done on the gas, so that means this work is negative, because the work is done on the gas. Okay, so we use work equals to P delta V, and the P is constant, okay, constant all the time. So we get P V2 minus P V1. Then we are going to substitute this into the we are going to use the next formula, PV equals to nRT. So for PV1 is nRT1. So we can see we can find temperature from this equation. So PV2 will be nRT2. So we substitute all the values here, okay, for PV2 also, and we combine both equation, and we get and also work done just now negative. Okay, so the temperature is 2.92 degrees Celsius. Okay, so the R here is 8.31. I didn't substitute, didn't show here. So the final temperature is 2.92 degrees Celsius. Okay, so you can write it in two significant figures. So write 2.9 degrees Celsius. Okay, 2.9 degrees Celsius. Okay, now we go to question 6. A gas has a value of gamma 5/3. Gamma is ratio of CPM to CVM. Okay, find the degree of freedom for the gas. So for degree of freedom, gamma here, we can use the relationship gamma with F. So the formula is gamma equals to F plus 2 over F. And because this is CPM over CVM, CPM over CVM. Okay, so we substitute 5/3 and cross multiply, we get F is 3. So if F is 3 for A, so that means the gas is monoatomic. Monoatomic. So you must memorize this. F3 for monoatomic, F5 diatomic, F6 is polyatomic. Okay, so next question, determine the molar heat capacity at constant volume, CVM. So we can use the formula CVM equals to half FR. Okay, so we substitute the F3, R is 8.31, so we get CVM 12.465 joule per mole per Kelvin. And for CPM, we use half. There are two methods. You can use the relationship between CPM and CVM. Okay, so CPM is CVM plus R. So we get 20.775 joule per mole per Kelvin. Or you can use CPM equals to half bracket F plus 2R. So there are two formula can be used. You will get same answer. Okay, so same answer. Okay, so next question 6, and that's the end of tutorial, this tutorial, and bye bye.